Hi everyone, welcome back. Hopefully, you're coming back from the last video. And so we're here to talk about stochastic processes some more. And so it turns out that there are, as you may imagine, there are different types of stochastic processes. Um, in our Shippensburg example, and so when I mean different types, I mean there are two sort of distinguishable things that we do in a stochastic process. One is what we calculate, or we're observing a variable, a random variable, and that random variable can be either continuous or discrete. And then we're also observing this random variable over time. And time can also be discrete or continuous. Okay, and so here are two examples that we've already done, and I'm going to compare and contrast them. In our Shippensburg example, we were observing a continuous variable, temperature, over a discrete time point. Or, sorry, it shouldn't be a discrete. It should be over discrete time points. Because we were observing it once a day at noon. Okay, so we've got continuous variable over discrete time points. Okay. And then in our space shuttle example, we are observing a continuous variable, again temperature, over a continuous time interval. We were observing the temperature continuously through the whole launch and all the way down from the launch to the landing of the space shuttle. And so that's over a continuous time interval. And it turns out you can have discrete variables as well. And then there are four different time processes, different value/time processes that we can have. So of course you could discrete, continuous, and then continuous, discrete, or discrete and continuous. Okay, so four different types. We aren't going to talk about all of them. In fact, we're only going to talk about a special case of some of them. But it's important to know that these can come up in different circumstances. And it really does affect the different types of random variables and probability distributions and all that stuff that's required for this. But we don't have the time to discuss all of it, so we're going to move forward. Okay, but just know that it's there. Sometimes we can have a finite number of random variables / probability distributions, but when it's continuous, really then it's an infinite number of probability distributions over time, and it gets theoretically and actually computationally or practically a little bit too complicated for this course. So what we are going to discuss is a couple special types of stochastic processes. And the first one that I told you a while ago that we would circle back to is called the Poisson process. So you'll remember the Poisson distribution was one of our discrete distributions that we talked about, where we're counting the number of things that happen over a given time interval. Okay, or rather, there wasn't anything special about a Poisson random variable other than it needed to have a rate associated with it. Okay, but usually we're counting something over time. And so that sort of matches up with what we're doing here. And it gives rise to a Poisson process. So it's a counting process, and the term counting process in itself has a formal definition. So I mean a counting process in a formal sense, not just that it's counting things, but it's a counting process that counts arrivals, whatever arrival means, during a given time span. So basically what the Poisson process is that the number of arrivals in any given time interval, and we denote that interval from t naught or t sub 0 to t sub 1, okay, is going to be modeled with a Poisson random variable. And if you remember, the Poisson distribution had one parameter, which was the rate, and it turned out that the rate was equal to the mean and the variance. Okay, but we're interested in the mean here. So the new mean is going to be the old mean, lambda, times that time interval, okay, or the difference of the time interval, which tells us how long it was, okay, where lambda is the rate of the arrivals per unit. Okay, and so it's really not that difficult, not that different from what we've been doing before we got to sort of this point, okay, but it's just that. Here's the PMF of it, and it's just the PMF of the Poisson distribution, but we've got now lambda lambda times t1 minus t naught. So it's got that difference in the mean. Okay, so given this PMF, we're going to now calculate some probabilities, as is usual with us, okay, with what we do in this course. So suppose, for our example, suppose that there are pulses that arrive at some counter that counts the pulses at an average rate of 6 pulses per minute. Okay, so I want to find the probability that at least one pulse is received in a 30-second interval. Okay, so to refresh our minds from what we just saw, the PMF which is sort of f of x, is equal to lambda times the time interval raised to the x power. Okay, really it's the whole thing raised to the x power. I missed that on the formal definition. Times e to the negative lambda, which is now lambda times t naught, t1 minus t naught, all divided by x factorial. Okay, and x can go between, or x can be 0, 1, 2, all the way up to countable infinity. Okay? And so I want to find the probability that x is at least 1, that I get at least one pulse in a 30-second interval. Okay, so now there's a couple different ways that we can go about this. The tough part here is that it's not explicit, or it's not easy to sort of guess what T1 and T naught are, but you always have to match the T1 and the T naught in their units to what the units of lambda are. So the units of lambda here, lambda is 6 per minute. So lambda equals 6. And it means that the average rate of pulses that the counter receives is 6 per minute. So it doesn't really matter what T1 and T naught are. What matters is that the given time interval here is 30 seconds. Okay? And 30 seconds means, or 30 seconds is equivalent to 1/2 a minute. So it turns out that T1 minus T naught, it doesn't really matter what the actual values are. All that matters is that that difference is equal to 0.5 or 1/2 a minute. Okay, so hopefully that made sense. It doesn't matter what T1 and T0 are usually when we do these problems. It only matters that the difference is equal to sort of what you're interested in. It's a 30-second interval. I know that lambda is taken in minutes, and so that interval, T1 minus T0, has to be in minute units as well, and so 30 seconds is half a minute. Okay, so now we have everything that we need. We have lambda, we have T1 minus T0, okay, and now all we need is x. And so when we look down at our problem, remember that the PMF is the probability that x equals a single point. Okay, and so I'm going to find the probability that x is greater than or equal to 1, at least 1. And so now you have to think back and remember our tricks, so to speak, that we used in the discrete distribution situation. And the trick is that possible x values are 0, 1, 2, all the way up to infinity. And so the only thing that is not greater than or equal to 1 is 0. Okay, that's the only thing that doesn't match that criterion. So I can find this probability by saying, well, what's the probability that x is greater than or equal to 1? I don't know. That's going to be really hard to calculate. But what I can calculate, and what this is equal to, is 1 minus the probability that x is 0. Okay, and this we can find with the PMF. Okay, so let's do that. Let's substitute it in. So it's going to be 1 minus, and now we need to substitute in x is 0, T1 minus T0 is 0.5, and lambda is 6. So what we get here is 1 minus lambda times 0.5, all raised to the 0 power, times e raised to the negative lambda, which is 6, times T1 minus T0, which is 0.5, divided by x factorial, which is 0 factorial. Okay, now, anything raised, so let's simplify things here. It's good. It's 1 minus, what's 6 times 5 raised to the, 6 times 0.5 raised to the 0 power? Well, 6 times a half is 3, and anything raised to the 0th power is equal to 1. So this first part here that I underlined, that's equal to 1. So it's going to be 1 minus 1 times e to the negative 6 times 0.5, so that's e to the negative 3. So I've got 1 times e to the negative 3 power, divided by 0 factorial, and 0 factorial is 1 as well. Okay, so really, this probability is equal to 1 minus e to the negative 3rd power. Okay, and it turns out that e to the negative 3rd power is around 0.5. Sorry, 0.05, and so the answer is 0.95. Now I'm going to just take a second here and do some quick calculations to see if that matches up. Yes, so e to the negative 3rd power is 0.0497. And so we just round that to 0.05. And so 1 minus, so this is e to the negative third is 0.05. Okay, not the whole thing, but e to the negative third is 0.05, so 1 minus 0.05 is 0.95. So there's a 95% chance that you see at least one pulse during a 30-second time interval. Okay, so I'm going to leave that here just for a second so you can write this down if you're not quite caught up, or you can stop the video. And so let's move on. And in fact, we're only going to move on to a your turn, which is the end of the video. And so here's the your turn. Another example that's similar to the one that we have here. Okay, although it's going to be a little different. Okay, a little different, and you're going to need to use Minitab to do it. Okay, so a web server receives hits at a rate of 10 hits per second. Using this information, find the probability that the server receives at least 1,400 hits in a 2-minute interval. Okay, so again, this would take forever if you tried to write this out by hand like we did in the last example. But you have Minitab, okay, and what you'll want to do basically is to translate 10 hits per second into a rate of a 2-minute interval. Okay, and then you can use Minitab like we've been used to using to solve the problem like we're used to solving it. Okay, so again, we'll go over this in class on Wednesday. And so that's the end of this video and the end of talking about Poisson processes. We'll have one more, a couple more videos on Friday that will discuss different processes.